In section 1.7, we talk about the library of parent functions as well as transformations of graphs. So our goal here is to try to recognize the basic shape of a function based on its equation and based on some simple transformations. So let's start with linear functions because we know what these look like. We've already talked about linear functions a lot. A linear function is going to be a function of the form f of x equals mx plus b. Remember, f of x is telling you the output or the y value for this graph. And so this is going to be an equation in slope-intercept form, where m is the slope and b is the y-intercept. So what this graph looks like is going to depend a lot on m, right? M represents the slope. That's the rate of change. And so we know that this function is going to be increasing, right, going up from left to right, when m, the slope, is positive. So when m, the slope, is greater than 0, when it's positive, this function is going to look something like this. It's also going to depend on the y-intercept, whether it's shifted up or down at all. If the slope is negative, we know that that line is going to be going downhill from left to right. You have negative slope, your graph goes downhill. It's a decreasing function. And when your slope is equal to 0, well, in this case, your function is just going to look like f of x is equal to b. Because 0 times x is just 0, that first term will go away. And so this, of course, is just going to be a horizontal line. Again, depending on what b is, it might be shifted up or down, but it'll be a horizontal line. Now, using what we learned in the last video, we can determine the domain of these functions. Remember that these are polynomial functions, and so the domain is going to be all real numbers for all of these. You can plug any x value you want into this function, and the output will be well defined. What about other types of functions, though? We've talked about quadratic functions a little bit. A quadratic function is a polynomial function where the degree, the largest exponent, is 2. And so our basic parent function here would be the function f of x equals x squared. And this looks like a parabola that has a vertex, that's sort of the low point, at the origin 0, 0. So this is the basic shape of the function f of x equals x squared. And again, it's a polynomial. We know that polynomials have a domain of all real numbers. You can plug any x value you want into that function and it will be defined. Now what about x cubed? So this is another polynomial. Since it's a polynomial, its domain is all real numbers. And it's similar, except that now we're raising x to the third power. And so for positive x values, it's going to look pretty similar to x squared. It'll just grow a little bit more steeply. But for negative x values, when you take a negative value, like -1, and plug it into this function, -1 cubed is still negative. It's -1 times -1 times -1. We have 3 copies of a negative number, so the output's negative. And so on the left-hand side of this graph, it flips down and heads off down towards negative infinity instead of positive infinity. All right, so this is what our sort of basic graph of f of x equals x cubed looks like. Call this a cubic function. Now what about the square root function? So square root function is going to be one where, okay, there's sort of an invisible 2 here. Oops, it's hard to read that. Right, there's an invisible 2 here because it's square root. And we saw in the last video that the domain of an even root function, and square root's an even root, is going to be, well, we would need whatever's underneath the radical sign to be greater than or equal to 0. So our domain here is a little different. It's all x values greater than or equal to 0. Or another way of writing that would be the interval from 0 to infinity, including 0, but including no negative values. And the graph of this is going to look like, well, 0, 0 is certainly going to be on this graph. And then it's going to grow kind of slowly in this direction. So this is what our square root function looks like. All right, what about a cubic root? Right now it's the third root, and so we had said that if it's an odd root, then there's no specific rules here. As long as what's underneath the radical sign is defined everywhere, then this domain would be all real numbers. In other words, you can plug in any x value you want here. The cubed root of any real number will still be a real number. So the domain is all real numbers. And again, this looks similar to the square root of x function. It grows a little bit slowly like this, except Remember, now it's defined on negative numbers as well, so it'll keep growing similarly in the other direction. So here's our cubic root function. All right, our next family of functions would be the absolute value functions. So f of x is equal to the absolute value of x. This is a function that takes the input and just, if it's positive, leaves it alone, and if it's negative, changes it to positive. Right? It takes a negative number and just makes it positive. If it's 0 or bigger, it just leaves it alone. So this looks like the graph of f of x equals x for x values that are greater than or equal to 0, and it looks like the graph of f of x equals negative x for negative x values. So it ends up being a V-shaped graph with a point right here at 0, 0. But again, the domain is all real numbers because you can plug any real number that you want into this function and it'll be well defined. All you have to do is just, if it's positive, leave it alone, and if it's negative, make it positive. But no matter what you plug in, that output will be well defined. All right, our last family of functions are reciprocal functions, something of the form 1 over x. Now this one's a little bit different because let's first think about what the domain would be. Remember, when you have an x or any sort of term in the denominator, we need to make sure that that denominator is never equal to 0. So we need x to not be equal to 0. That means that the domain is going to be all real numbers except for 0. And what this ends up looking like is something almost sort of L-shaped up here in the first quadrant. And down here in the third quadrant, we have a similar shape, but sort of reflected down here. All right, now we call this a vertical asymptote, and we'll describe this a little bit more carefully in a future video. But essentially, these arrows that are approaching the y-axis, they're getting closer and closer and closer, but they're never actually touching it because we know that the function is undefined when x is equal to 0. Similarly, these arrows, as x heads towards positive or negative infinity, the graph is heading towards an x value of 0, but it never exactly reaches it because we know that 1 over x could never be equal to 0. There's no x value you can plug in that will give you an output of 0. So this is a graph that has two asymptotes, a vertical asymptote and a horizontal asymptote. Now, we know what these basic shapes of these functions look like. What if the function's a little bit more complicated than just x squared or just square root of x, etc.? For that, we need to understand how to transform a function, right? How to take a particular graph and move it around in some way. Let's say you have a particular function f of x, and you want to shift the graph of that function up some units, c units. So c is just some real number here. If you wanted to shift the graph up c units, all you need to do is define a new function, which is just going to be your original function plus c. All right, similarly, if you wanted to shift your graph down c units, just take a new function, which is your original function minus c. So to show you what I mean here, consider the function h of x equals x squared plus 3. We can start off by graphing the original function. Oops, let me zoom in so I have space here. Let's graph the original function f of x equals x squared. Try that again. F of x equals x squared. We know from earlier in the video that this is a parabola. Should go right through the origin. But we want to graph x squared plus 3. So according to this rule up here, x squared plus 3 is just going to be the x squared graph shifted vertically up 3 units. And so instead of having a point here at 0, 0, I'm going to shift it up 3 units. 1, 2, 3. And this is what your new graph will look like. It's that same basic shape, but it's been shifted up 3 units. All right, so I started with my parent function, x squared, and when I add 3, I take that parent function and I shift it up 3 units. Let's try another example. If we wanted to graph, this is a graph of x squared plus 3. If we wanted to graph the function h of x, which is 1 over x minus 2, remember, 1 over x looks like this on its own. Right? We saw that 1 over x was this reciprocal function that looks like this. So I'm going to start by letting f of x be that reciprocal function, 1 over x, that I already know what it looks like. Right? This sort of roughly L-shaped thing. with this horizontal asymptote. Oops. Oh no, what have I done? All right, try it again. All right, this is my original f of x function. I have vertical asymptote and a horizontal asymptote. There we go. And now we want to graph the function 1 over x minus 2. So according to the second rule up here, this is going to be the graph of 1 over x shifted down 2 units because we subtracted 2. So I'm just going to take this horizontal asymptote and move it down 2 units to negative 2. I haven't shifted left or right at all, which means my vertical asymptote will stay the same. And so I have that same basic L shape, but I've just shifted my horizontal asymptote down 2 units. So now my graph looks something like this. Alright, so just to summarize, if we want to shift a graph up or down, just take your original function and add that constant term, whatever it is you want to shift up or down, add it to the end to shift up, subtract it to the end to shift down. Alright, well what if we wanted to shift our whole graph left or right? Okay, if we want to shift the graph of f of x to the left c units, we're actually going to, be careful here, what we're going to do is we're going to replace x with x plus c. Right? So this is a little bit misleading, right? We're going to the left. In general, when we think of moving to the left, it seems like subtraction perhaps, but we're actually going to replace it with x plus c to move the graph to the left. Then, if we wanted to shift our graph to the right, we're going to replace x in that function with x minus c. Okay? Alright, how is this different from the vertical shift in the last one? Well, in the last page, let me go back a page, that plus c and the minus c was outside of the f of x function. So we just took the original function and then tacked on a constant at the end. This is different because now we're saying replace x in the function with x minus c. So let's see how that works here. I'm going to look at this first graph. I have an original function of x cubed. I know what that looks like. X cubed looks something like this. And now, what we've done here is we've replaced x in the function f of x with x plus 2. Okay? So essentially what we have here is the function f of x, but we've shifted it left 2 units, right? Because we've replaced x with x plus 2. When you replace x with x plus 2, that means you need to shift it to the left 2 units. So instead of hitting the origin, like we have here, we're actually going to move 2 units to the left, over here to negative 2, and then draw that same graph that we had, but shifted over 2 units. Alright. If we had wanted to shift it up 2 units, we would have had something like x cubed plus 2, where the plus 2 was separate from the x term. Since it's attached to the x term, that's how we know that it's going to be a horizontal shift rather than a vertical shift. Alright, let's look at another example. I'll try and separate these two here. Alright, so now what we want to do is we want to graph the function h of x, which is the absolute value of x minus 4. So our parent function here is going to be the absolute value function, which we know is just a V-shaped graph like this. But the graph that we're trying to produce is what have I done? Let's come back for a sec. Is the absolute value of x minus 4. So we can see that we took x and we replaced it with x minus 4. This should be an absolute value bar. Right? So because the minus 4 is inside the absolute value bars with the x, that's how we know that this is a horizontal shift rather than a vertical shift. And because it's x minus 4, that means we're using the second rule here. And that means that we're going to be moving it 4 units to the right. Right? So replacing x with x minus 4 is going to shift our graph 4 units to the right. So let's try that. So just take that sort of center point here and move it 4 units to the right. 3, 4. And our new graph looks like this. Alright. What other kinds of transformations could we do? Well, another thing that we could do is we could try to reflect our graph. So let's say we wanted to reflect a graph across the x-axis. Remember, the x-axis would be this one here. Okay. The way that we reflect a graph across the x-axis is we take whatever our original output was and we make it negative. Or if it started negative, we make it positive. And so if we wanted to reflect the graph of f of x across the x-axis, we would just need to take that entire function and make it negative. On the other hand, if we wanted to reflect our graph across the y-axis, this time you just change the sign of x. So you don't make the entire function negative, you just make the x part negative. Or take any instance of x and replace it with negative x. That will reflect your graph across the y-axis. So let's do some examples. Our parent function here for this h of x is going to be f of x is just the regular square root of x. And we know from previous pages that that looks like this. Now we've taken that function f of x and made it negative. So h is just negative square root of x. So we're in this scenario up here where we took the entire function and made it negative. That means the resulting graph is going to be reflected across the x-axis. So that's going to look like this. Okay. What about in the second example? So in the second example, it's going to be the same parent function. We're still going to start with f of x is the square root of x. But now, we've replaced x with negative x. That is, our h of x is going to be f of negative x. So now we're in the second scenario here. The negative sign is with the x, it's underneath the radical sign. And so the result of this is going to be the result of reflecting this graph f across the y-axis. Here's our y-axis. When we reflect it across the y-axis, when we flip it over, it looks like this. So square root of negative x looks like this graph here, this last one. Now this is all well and good. We know how to reflect graphs, we know how to shift them horizontally and vertically, but sometimes you'll see graphs that are a combination of these, graphs that have been shifted both vertically and horizontally and potentially also reflected. So let's do a couple of examples of that. Right? So say we wanted to graph 1 over x minus 2 plus 3. So there's two transformations that are happening here. First of all, we have x is being replaced with x minus 2. This part here is going to represent a horizontal shift. And then we also have a plus 3 at the end. That's going to represent a vertical shift. Right? But our parent function is just plain 1 over x. Whoops. Try that again. Our parent function is 1 over x. And we've seen that that looks like this, with our horizontal asymptote and our vertical asymptote. All right, now I'm working my way up to, I guess I should be careful about calling this f of x, because f of x, we said up here, is the entire function, 1 over x minus 2 plus 3. So I probably shouldn't call this parent function f of x again. We don't want to give two different functions the same name, at least not on the same slide. So I'm going to call this f1 of x, just to say it's a little bit different. Right? We're building up in stages. So that's going to be our parent function, f1 of x. f2 of x, just to demonstrate the next step, would be 1 over x minus 2. Right? Remember, we said replacing x with x minus 2 is going to represent a horizontal shift. Right? Just a plus a constant at the end represents a vertical shift, but replacing x with x plus or minus a constant gives you a horizontal shift. And because it's x minus 2, I should use a different color there. Because it's x minus 2, this is going to be a horizontal shift to the right. So shift 2 units right. Okay, so 2 units right means my vertical asymptote is now going to move over to 2. My horizontal asymptote hasn't changed yet because I haven't done a vertical shift yet. And so when I shift this 2 units to the right, my new graph looks like this. All right, and now finally, I can graph my final graph that I'm looking for, this one. I just need to take f2 of x, the most recent graph, And because there's a plus 3 at the end, I need to take f2 of x and shift it vertically 3 units up. All right, so this is when our horizontal asymptote gets shifted up 3 units. It's going to go up 1, 2, 3. Our vertical asymptote is going to stay where it is at x equals 2. And then we can actually draw in this graph. Whoops. This wasn't very well done. I didn't leave myself a lot of space, but the graph's going to end up looking like this. Something like this. All right. Let me do it in another color just to make sure it's clear. The graph ends up looking like this, with a horizontal asymptote through y equals 3 and a vertical asymptote through x equals 2. All right, we'll do another example. Let's say we wanted to graph the function f of x is negative square root of x plus 1 plus 2. All right, there's a variety of things that are happening here. There's a negative on the outside, which represents some kind of a reflection. There's a plus 1 on the inside of the square root, which is going to represent some sort of a horizontal shift. And then there's an added constant term at the end that's going to represent a vertical shift. So our parent function, hopefully it's clear that parent function is, let's call it f1 of x, is just plain square root of x. So we know what that looks like. That looks something like this. Now we're going to try to transform it into this end function, the negative square root of x plus 1 plus 2, one step at a time. So I'm going to start with the term that's closest to x, or with the transformation closest to x, which would be, I'll call this next function f2 of x, which is square root of x plus 1. All right, now this is like the f1 function, like the square root of x function, but x has been replaced with x plus 1. When you replace x with x plus 1, you shift the graph horizontally 1 unit to the left. Right, a plus 1 represents a left shift. So we're going to left shift by 1 unit. Oh boy, what have I done? 1 unit. So instead of having a point here at the origin, I'm going to have a point here at negative 1 because I've shifted it 1 unit to the left. The shape's the same, it's just been shifted 1 unit to the left. All right, now let's think about this negative sign on the outside. So for my third graph, I'll call it f3 of x. I want to try to graph negative square root of x plus 1. So I'm going to take that f2 graph, the one that I just drew in the last example, and a negative on the outside means that I reflect it over the y-axis. So I need to reflect the f2 of x function, over the x-axis. Right, y is at the x-axis. Let me go back to explain why. Here it is, right? When you have a negative on the outside, you reflect across the x-axis. So I'm going to take that original graph f2 of x and I'm going to reflect it across the x-axis, that's this one, and now it's going to be heading off in this direction. Right, reflect over the x-axis and the result is this. Finally, the last thing that I'm going to do, let me choose a different color just to differentiate. If I want to graph our final function here, negative square root of x plus 1 plus 2. I'm going to need to take my most recent graph, that's f3 of x, and I need to shift it, shift f3 of x up 2 units. Because we have a plus 2 at the end of the f3 function. This is our most recent function here. Now we're adding 2 to it. That means we're going to have a vertical shift. So it's going to be that same basic shape here at negative 1, but shifted up 2 units. So now I'll have a point at negative 1, 2, and it'll keep going in this direction. All right, we'll do some more examples of transformations of graphs in class.